Hello and welcome to the AICE Chemistry lecture series. In this video, we're going to look at chapter 15, section 6, which is simply a section to address the different kinds of questions you will be asked on the AICE exam about addition polymers and addition polymerization. Addition polymerization is one of those topics that's very new because it doesn't create individual molecules, it creates large polymers. And so we want to spend a little bit of time discussing the 2 or 3 different types of questions that you could see on the AICE exam about this topic. So let's get started. With addition polymerization, the AICE exam is mainly going to ask you 2, maybe 3 different types of questions depending on how you view it. First type of question you will be asked is to deduce the repeat unit of a polymer obtained from a given alkene. Meaning that they'll give you an alkene and they'll tell you this is the monomer and they'll ask you to draw a repeat unit of the polymer that results from that monomer. The other type of question, which is essentially the opposite, is to identify the monomer in an alkene or in a polymer given a section of the polymer. So they will give you the polymer, they will give you the product, and then ask you what is the monomer alkene. Now, the reason why I say 2, maybe 3 different types of questions depending on how you view it, is that addition polymers can also be produced from more than one monomer. So sometimes we can have 2 different monomers reacting with each other to create a polymer. So polyalkenes are usually going to be made from one monomer, but you may see questions where they're made out of 2. And so you need to be careful as to what is going on with those monomers. So for example, if we were to make an addition polymer from these 2 monomers, what we will see is that we will get a repeat unit with 4 carbons. Why? Because this monomer and this monomer are different. When this double bond breaks, when that double bond breaks and this carbon joins with this one, and then this one breaks to join the next one, we end up with a repeat unit that has 2 different sections. The first section being the 2 carbons from the initial monomer, which I highlighted here in yellow, one of which has a phenol, a benzene ring attached to it. And then the other section coming from the second monomer, the second 2 carbons, which both have hydrogens and one has a chlorine. So we'll see kind of this alternation of carbon, carbon with benzene, carbon, carbon with chlorine. And then that will keep going on and on. So whereas most addition polymer monomers have 2 carbons, or most addition polymers repeat units have 2 carbons, this one will have 4 carbons because it's made of 2 different monomers. And that's why I say that there's 2, maybe 3 types of questions, because in reality there's only 2. There's giving you the monomer and ask you what the polymer will be, and then giving you the polymer and then ask you what the monomer is. But again, that one, it could end up being more than one monomer. So let's look at some examples. Imagine we have 2-butene as an example, and we're going to tackle first the questions for writing the repeat unit of a polymer when you're given the alkene. So imagine we have 2-butene, which is just a simple 4-carbon chain with a double bond on the second carbon. If we were asked to figure out what polymer we are going to make out of this monomer, what repeat unit will be, the very first thing you want to do is convert your skeletal formula to a display formula centered around the double bond. So essentially we will look at this and say, okay, so the double bonds here, we have this carbon and this carbon on the double bond. And we will look at what is attached to those carbons. This carbon right here has a CH3. Let me make that smaller. Has a CH3 here and a hydrogen, which we're not seeing. And this one has a hydrogen and a CH3. So when we make this skeletal formula into a displayed formula centered around the double bond, we will put the carbons with the double bond and then put the 4 groups around them. Keep in mind, look at how this is structured. This is a trans isomer. The CH3s are on opposite ends, or the hydrogens are on opposite ends. So we would redraw that as a trans isomer, the carbon double bond, with a hydrogen and a CH3 on one carbon, hydrogen and CH3 on the other, with the CH3s across from each other. That's our first step to drawing the repeat unit. The second step to drawing the repeat unit will be to turn the double bond in the monomer into a single bond. Why? Because during polymerization, during addition polymerization, the pi bond in the double bond breaks. So the next step, once we have this displayed formula with the double bond in the middle, we will get rid of that second bond in the double bond. Turn the double bond into a single bond. And that's going to create a part of our polymer. Because remember, our polymers for polyalkenes don't have double bonds. The alkene they're made from has a double bond, like this one, but the polymer itself does not. So we turn the double bond to a single bond as the pi bond breaks. And then the last step is going to be to add single bonds to the opposite sides of the carbons. Remember, we're drawing a repeat unit of a massive polymer. That's going to keep going in both directions. So we're going to draw our bonds at either side of our polymer, and then what we normally do in class, although this part is technically optional, but what we do in class is that we also are going to use brackets and the subscript n to show that this is a repeat unit. So once we go from that single bonded carbons, because we got rid of the double bond, to then drawing those bonds on each side of the carbons, we're going to put a bracket with an n to show that this is a repeat unit of a much larger polymer. And that's how we go from the alkene all the way to our repeat unit. So again, we grab our alkene, we center it around the double bond and put the 4 bonds that those carbons are going to have, or 2 per carbon. We break the double bond and make it a single bond. Then we add bonds to each carbon, and then we add the bracket and with an n to show that this is a repeat unit of a much larger polymer. So that's how we go around tackling the question of how does a polymer get created from an alkene monomer. If we had 2 monomers, we'll do the exact same thing, only we will then join them with that bond. Now, what about the other question? Identifying the monomer present in a given section of a polymer molecule. So what if we get the opposite? What if we have a polymer and realize that they're not necessarily going to give you a repeat unit here? We are going to have multiple repeat units, and you can see because we have multiple chlorines or multiple CH3s of our polymer, and they're asking us what is or are, if there's more than one, the monomers. So how will we go around doing this? Well, it's the exact opposite steps. We have our polymer. The very first thing we need to do is identify the repeat unit. We're going to identify and isolate the repeat unit of the polymer. So we're going to look at this big polymer, and we are going to say, okay, where does it start repeating? Which section of this can I copy and paste, and to make this larger polymer? And that's right here. So the best idea here is to start at our bracket and then go and box in the whole molecule right before you see that next carbon again. So the first carbon in this repetition that they gave us is this carbon right here, which has a chlorine attached to it. So we're going to use that chlorine as a landmark. We're then going to box in everything up till the bond before that same carbon with the chlorine starts again. So that's going to give us our 1 repeat unit. So we're going to isolate that. So where we drew those lines, we're going to put our brackets. So we're going to isolate that section, and that's our repeat unit of our polymer. But we're being asked not for a repeat unit, we're being asked for a monomer. So how do we do this? If the repeat unit has a backbone, and remember the backbone, we are referring to the carbon chain at the center of our polymer. So this is our backbone. So if the backbone of our repeat unit has more than 2 carbons, then we're going to split it into 2 sections, because that means we have more than 1 monomer. So in this particular case, if we look at this, we have 1, 2, 3, 4 carbons. Because we have 4 carbons, we know we have 2 monomers. Remember, the backbone of a polymer for addition polymerization is going to have 2 carbons per monomer. So if we have 4 carbons in total here, that means that we have 2 monomers. So we have 2 here, 2 here. So we are going to split them into those 2 sections. We're going to split this repeat unit that we got into 2 sections. The one on the left with the 2 carbons where one has a chlorine and the other one has 2 hydrogens. And the one on the right where one has 2 hydrogens and the other one has a CH3. So that's our blue carbons are right here. And then our red or pink, whatever color you want to call this, carbons are right here. Let me erase this from before. So we broke down our repeat units even further into a 2 monomer sections. Because that repeat unit have 4 carbons, this polymer had to be made from 2 different monomers. How do we identify those? Again, we look for landmarks. We have the same carbon with the chlorine there and the carbon with the CH2. And then that bond that went to this carbon right here, which has CH2, and then the carbon with the CH3. The next step, and now once we get here, we're just working backwards from what we did in the prior problem. We are going to now get rid of the single bonds on either side of the carbon backbone. So we're going to grab the double bonds that go through our brackets. So this, the single bonds that go through our brackets. So this single bond and this one, and then this single bond and this one, and we're going to get rid of those because remember, we created those to make the polymer. Those are created during the addition polymerization reaction. So what we're going to do is we're going to get rid of those. We're going to rewrite these molecules without those bonds. So this is going to be 2 carbons with a chlorine on the first one. This is going to be 2 carbons with a CH3 on the second one. You see how we're just getting rid of those bonds and the brackets? And then once we have that, all we need to do is to recreate the double bond between the 2 carbons in the backbone. So we're going to recreate those double bonds, and now we have our 2 monomers. We have our monomer on the left, which is 2 carbons, so it's ethene. So it's chloroethene. And then this one, which has 3 carbons, so this is propene. So you have ethene or chloroethene and propene as our carbon, our monomers, alkenes. So obviously, if we only had 1 carbon monomer or 1 alkene monomer in our polymer, then we will do this, only we wouldn't have had to split up the 2 monomers in our repeat unit. Our repeat unit would only have 2 carbons if there was only 1 monomer. But because this one has 4, then we have 2 different monomers. So that's it. That's it for polymerization, how to tackle the questions. There's only 2 really real type of questions you're going to get beyond just what type of reaction is this, which will be addition polymerization. So that's it for chapter 14. Now, at the end of every chapter that has reactions that we need to memorize in organic chemistry, we are going to see one of these in the PowerPoints. These are our what we call reaction webs, and they address all of the different reactions that we saw in the chapter put together so we can see how all of the reactions can form different things. Now, how are we going to read this? First of all, these are not going to use specific compounds. They use functional groups. Because remember I told you, the best way to view organic chemistry reactions is by the functional groups they create. So here we have our functional groups instead of our reactants. Alkenes, alkanes, polyalkenes, diols, two OH alcohols, dihalogenalkanes, which have two different halogens. We have alcohols up here, halogenalkanes up here. And those are going to be connected by arrows. Now, the color of the arrows is going to dictate the type of reaction we are looking at. So here we always have a key that tells us the different types of reactions in the chapter. So we can see that red arrows are combustion reactions. Pink arrows are addition polymerization reactions. Addition polymerization reactions here. A purple arrow is free radical substitution. Oxidations are in green. And addition mechanisms and addition polymerization reactions are in blue. And if we need to know the mechanism for a specific reaction, that is set here. So combustion, oxidation, and addition polymerization, we do not need to know the mechanism for those reactions, although addition polymerization is basically the same mechanism as addition reactions. But for free radical substitution and for addition, we do need to know the mechanisms. And then it's a matter of just having the reactants on top of each arrow. So for example, in order for an alkane to become an alkene, we will need to react them with aluminum oxide under heat, but with no oxygen. So if we wanted to grab an alkene and turn it back into an alkane, we will react that alkene with heat and a nickel or platinum catalyst. If I wanted to turn an alkene into a dihalogenal alkane, I would use either chlorine or bromine aqueous to do that. So here is how these reactions work. If I wanted to, for example, go all the way from an alkane to a diol, how would I do that? Well, I would just follow the arrows. If I wanted to turn an alkane into a diol, I will have to first do a reaction where I turn an alkane into an alkene using aluminum oxide, heat, and no oxygen to turn that into an alkene. And then I will grab that alkene and react it with acidified dilute potassium permanganate to make it into a diol. So what these have or make are reaction pathways, which are when we do multiple reactions in sequence, very easy. The only thing they don't show is our observations. For example, here on the left side, we learned that when potassium permanganate reacts with alkene, we go from purple to colorless. That's not shown in these pathways because what these pathways are for is for the reactions, not so much the observations. You should still obviously know the observations. So we're going to have one of these for every one of the chapters that we have left, 15, 16, 17, and 18, showing all of the different reactions that we learn in that chapter. And then at the end, we'll put one together for all of organic chemistry. That's it. That's it for chapter 15. And for the section specific of chapter 15, I will see y'all in our next video to start chapter 16, and look at halogen alkanes.